Hi calculus students! This is the final video that I am making on estimating area with finite sums. We are learning one final method. So far we've learned three methods. The right triangle method, the right rectangle method, the left rectangle method, the midpoint rectangle method, and then our last one is new, it's trapezoids. And so this page kind of just summarizes the four different methods and kind of gives you a visual about what each of them will look like. Okay, so you can think of this as like a summary page. Just a reminder, what each of these methods is doing is approximating the area given by a definite integral. So the definite integral is the exact area. And then the picture on the right, we can shade the area that we're trying to find. So since the integral, its a value is 1 and its b value is 5. 1, 2, 3, 4. Oh no, there's 5. 1, 2, 3, 4, 5. The area that we are finding with this integral would be the area in between these two values. So we can just shade this in to show we know what we're talking about. Let's see. Here's the area we're trying to find. And the integral, the definite integral, gives us the exact value. But we could also use approximation methods like they did in the old-fashioned days. So below are the four methods. And then there's kind of some summary statements about when each one underestimates or overestimates. So some multiple choice questions that come up on the AP exam often give you like a picture of a graph and asks you if it will be an overestimation or an underestimation. And so one thing I recommend is whenever you have a graph and are asked these questions, do a little sketch to help you figure it out. But otherwise we'll give you some rules of thumb. So for right rectangles, it is an underestimation whenever f of x is decreasing. So you can see right here, f of x starts decreasing and all the rectangles are underneath. They are an under approximation. But on this left side of the graph right here, when it's increasing, when f is increasing, the rectangle is above and it is an over approximation. Cool. And then left rectangles are the opposite. So it's an underestimation right here where f of x is increasing. The rectangles are underneath. But then the portion of the graph where f is decreasing, the rectangles are above, so they are an over approximation. So left rectangles overestimate when f of x is decreasing. Midpoint rectangles and trapezoids, which are kind of like hybrids of the left and the right approximations, are a little bit differently. You don't so much look at whether it's increasing, but you look at the concavity of the graph. So I can see this graph is concave down, and for both increasing and decreasing parts of f, the rectangles are over approximating. And so we have an overestimate, like the one above, when f of x is concave down like a frown. And then it's going to underestimate when f of x is concave up. Okay? Trapezoids are the opposite. So you can see with this concave down graph, the trapezoids are all underneath the graph. So all the trapezoids end up being underneath the graph. And so this is an underestimation when f of x is concave down. If I were to have a concave up graph, you would see the opposite. All of the trapezoids would be above the graph and they would be overestimates. If you have trouble on this sort of question, I recommend just drawing in a rectangle or a trapezoid, whichever one it's asking about, to help you help you determine if it's an over or an underestimate. Okay, on the next page, we're going to go through two examples. So a graphical as well as an equation as well as a table example. Okay, so they give you this kind of review of the area of a trapezoid at the top. So it reminds you that, well, maybe you weren't even aware of this, but the area of a trapezoid is 1/2 the bases. So it kind of takes the averages of these bases, 1/2 base 1 plus base 2. So it's the averages of the bases times the height. Our trapezoids, if we look back on this previous graph, these trapezoids are actually standing vertical instead of sitting down horizontally. And so we actually have to draw kind of different trapezoids that are more vertical. And so the trapezoids that are in our problems will look more like this. So they'll either look like this, like that, or they might look like this. But we have more vertical trapezoids. So we're actually going to use this equation more. So we'll have our base, and then the averages of our two heights. So these are what our trapezoids will look like. We take the average of the height, multiply times the base. Okay. Right here is kind of just a breakdown of the equations. So for instance, I have 1/2 the base, because that's going to be a part of all the equations. And then it shows like adding up the different sides of the trapezoids. So this is showing adding up 4 trapezoids. So 1 trapezoid, 2 trapezoids, 3 trapezoids, 4 trapezoids. And we could do that work every time, but it actually can be simplified a little bit. If you notice, some of the numbers appear multiple times in each of the equations. So it's the insides of the trapezoids, inside sides of the trapezoids that get added twice. So you see that they kind of simplify the math there. So what is happening, if I were to add up these heights, H1, H2, H3, H4, and H5, these heights on the inside share, they are heights for 2 trapezoids. So H2 gets counted both for this trapezoid, this first trapezoid, and it also gets added for the second trapezoid. And then H3 gets added for the second trapezoid as well as the third. So all of these middle heights end up getting added twice, which is why we can kind of simplify our equation to look like this one right here. Okay? And that is the equation that I'm going to be using in the next 2 examples. So, example 5 says approximate the area of the region bounded by the graph y equals -x squared plus 4, and the x-axis from 0 to 2 using 4 equal subintervals and the trapezoidal method. So I'm going to do that quick graph. 1, 2, 3, 4, from 0 to 2. The graph looks like this. At 1 it would be at 3, and at 2 it's at 0. So this is an upside down parabola like that. I need 4 equal subintervals. So my change in x is going to equal my b, which is 2, minus a, divided by 4, and that equals 1/2. So my change in x is 1/2. So I know that all of my rectangles are going to occur at those places right there. Okay. So in order to draw the trapezoids, I go up and just connect to the graph. That. and then I connect those points. I'll do it in red so it kind of stands out. So when I connect these points, you can see there is one trapezoid. This one will be a little bit more clear because it kind of goes down. There's my second trapezoid, my third trapezoid, and then my last trapezoid actually ends up being a triangle. But it works out the same. We still use the same area for a trapezoid. Okay. It's sometimes helpful to make a nice little XY table to help keep track of these. So I know I need heights at 0, 0.5, 1, 1.5, and 2. And so the heights I'm going to use this equation, and my y values are representing the heights of my trapezoids. So when I plug in 0, I get 4. When I plug in 0.5, I get 3.75. When I plug in 1, I get 3. When I plug in 1.5, 1.75. And if I were to plug in 2 into my equation, I get 0, this point right there, 0. Okay, so now I have my y values, my heights. I have my change in x. It's 1/2. And so now I can plug into this equation right there. Okay. So I know that the ones that I'm going to use twice, I'm going to make a little reminder. Those use twice because they are the inner walls of the trapezoids, and they get used in both the left and the right trapezoid. Okay, so here's my area. Oops, my area. So I need to multiply my 1/2 times the base. My change in x is my base right here. The change in x represents the base of each trapezoid. So 1/2 times 1/2. And then I'm going to start adding the heights. So 4 plus 2 times 3.75. That one gets added twice. Oh, I need to start writing smaller. Plus 2 times 3, I'm out of space, plus 2 times 1.75, those are the 3 that get added twice, and then plus 0. This ends up being 1/2 times 1/2 is 1/4. All the stuff in the parentheses was 21, so the area is 21/4. That's the trapezoidal rule. Key equation being this one right here. All right, let's look at what this is like with the table. So I'm estimating this integral from 0 to 6. I can see my table goes from 0 to 6, so I'll be using all of these numbers. And I'm dividing using 3 equal subintervals in the trapezoidal method. And so 3 equal subintervals means I'm going from 6 to 0 divided by 3. This is my change in x, equals 2. Okay. So each are going to be 2 in length. So I know my first trapezoid will go from 1 to 2. My second trapezoid continues from 2 to 4. And then my third trapezoid goes from 4 to 6. So these are the y values that I'm going to end up using. Those are my y values that I will use. Those are the heights of my 3 different trapezoids. And this one in the middle, I use twice because they are the sides of 2 trapezoids, where the ones on the end are only the heights of 1 trapezoid. So I'm going to use that same A equation. So it starts off with 1/2 times my base. That's my base. My change in x is my base. So times 2. And then start adding up the heights. So 9.3 plus 2 times 8.3 plus 2 times 2.3 plus negative 10.5. Add everything up, I end up getting 20. And that is my area. That is it. So big thing about the trapezoid, you use a slightly different equation because we're using areas of trapezoids rather than areas of rectangles. Key thing is that trapezoids have two different lengths for their heights, and so when we add them up, we end up adding all the heights in the middle up twice, which is why we get these 2's right there. That is the biggest difference between adding the rectangles and adding the trapezoids. Trapezoids, the reason why we use them is because they're way more accurate. Look at how using both points, basically we're using both the left and the right points. So instead of choosing the left or the right, a trapezoid is the best of both worlds. We use both the left and the right. And so it ends up being way more accurate. It's the most accurate of these techniques, which is why it was invented, and it will indeed come up on your AP exam.